Alright, now we move on to the sum, difference, and power rules of logarithm. The sum rule of logarithms simply says that if you have some logs that you're adding together, you can, instead of adding them, write them as multiplication. So if I have log base a of n plus log base a of m, have some logs that are being added together, but this should be an m. Then this is simply a log base a of n times m. My two logs become 1, and then I keep the base. This works both ways. I could take this right here and write it as a single log, or I could take this and split them and write them as two different logs. Similarly, if I have log base a of n minus log base a of m, I can write this log base a, and then I'll be dividing n over m, like so. Go ahead and divide. Again, because of the minus sign right here, instead of multiplying, I'm now dividing. And again, this works both ways. This right here is called the difference property of logarithms. Again, they work both ways. If I have two logs or more, I can change them into division. And the last property is the power property. And the power property says that log base a of m to the r power. If I have a power or an exponent right here, I can take that exponent and bring it out front. Log base a of m. This actually is a very important and powerful rule, but it is a nice simple way to go ahead and get your logs all simplified. Alright, so when it comes to logs and your power rules and you summon different rules right here, there are several questions that they love to ask. So let's start some simple ones. So express as a sum or difference of logs, and then you want to express powers as factors. Okay, here for this problem right here, they will give us a single log. So let's say log base 2 of 2x to the 4th power multiplied by z to the 9th power right here, and they want me to go ahead and simplify this right here. Well, if you look very carefully, you'll notice that I have three things being multiplied together. A 2 multiplied by an x plus 4 multiplied by a z to the 9th power. Therefore, this will split into three separate logarithms based upon each of those terms. And so I will get a log base 2 of 2 plus a log base 2 of x to the 4th power plus a log base 2 of z to the 9th power. So each of those terms gets their own log base 2. You can kind of think of it as distributing the log base 2 in there, although that's not what's actually happening. But that's how you can kind of think of what's happening right here. So each of them gets their own log base 2. And now they want us to simplify. They say, well, each of these powers right here, go ahead and make them a factor by using the last property of logarithms up here. And so this right here is equals to log base 2 of 2 plus 4 times log base 2 of x plus log 9 times log base 2 of z. And with that being said, I need to see if anything simplifies. Well, log base 2 of 2, we've come across this property already. When you have the log base and this term being the same, this log is equal to 1. And so then the fully simplified expression is going to be 1 plus log 4 times log base 2 of x plus 9 times log base 2 of z. We have taken this log and we've expressed it as a sum and difference of groups of logs. Let's try another example. Again, expressed as a sum of log right here. And so I have log base 5 of 25 x to the third power divided by b to the 11th power right here. And I am trying to simplify this. So again, what I do is I look at the log and I split it up. Well, I get 25 times x cubed and I have it b. So that's 3 terms. And so now I got to split this up. The rule of thumb to help prevent you from making errors is that you should always take the terms in the numerator as a positive log and the terms in the denominator as a negative log. And so this right here, it will going to be log base 5 of 25 plus log base 5 of x to the third. Notice both of these are positive because they come from the numerator, a plus sign or a node sign in front of them. And then I will have minus log base 5 of b to the 11th power. Okay, notice all of them have that same log base 5, so it's kind of like distributing the log base 5 in there. But because the b is from the denominator, the b is negative. Of course, I now need to bring the powers down and simplify as much as possible. And so this is log base 5 of 25 plus 3 log base 5 of x minus 11 log base 5 of b. And of course, no, not of course, but the log base 5 of 25, that's equals to, let's do this over here, log base 5 of 25 is log base 5 of 5 squared. So this right here is equals to 2 because all of this will cancel out. The log and the exponent cancels out. And so my answer is simply 2. So this final answer is 2 plus 3 log base 5 of x minus 11 log base 5 of b. Alright, let's try one that's a little bit harder, but follows through on the same principles. Let's say I have log base 8 of x to the 4th power multiplied by y plus 1 to the 5th power divided by the 4th root of z squared multiplied by m to the 7th power. Whew! Oh my goodness, right. Well, the first thing you want to do is you want to go through and split them up. X to the 4th is its own term, y plus 1 is its own term, the 4th root of z squared, let's make that z cubed, make that a more better explanative example. But again, it splits right here, and so I have 1, 2, 3, 4 terms. And so when I break this out, I'm going to get 4 separate log base 8s. And so this is going to be equal to, watch carefully now, log base 8 of x to the 4 plus log base 8 of y plus 1 to the 5th minus, open parentheses, and then I have my 2 terms in the denominator, log base 8 of the 4th root of z to the 3rd power plus log base 8 of m to the 7th power. I distribute my minus sign. That gives me log base 8 of x to the 4 plus log base 8 of y plus 1 to the 5th minus. And I just get 2 minuses right here. Which takes us to a very important rule. Again, whenever you are in the denominator, your log will end up being negative. Even though these two things are being multiplied together, because in the denominator the minus sign takes hold, and so you get that negative sign ending up right there. Which means there's a nice little shortcut. You just count how many you have in the numerator. That tells you how many positive logs you have. You count how many you have in the denominator, and that tells you how many negative logs that you will have. So with that being said, I got some work to do here. So I take the powers out front, and so that is 4 log base 8 of x plus 5 log base 8 of y plus 1 minus, this is a special term. Let's remind ourselves. When we have a radical, we can write this right here as a fractional power, 3/4. Remember, the 4 becomes the denominator right here. When you have your rational, the 4 goes under the 3. Remember that? And so this right here has a power of 3/4, and so 3/4 will end up in front of the log of z minus 7 log base 8 of m. And there you go. I have my log all split up into its millions and millions of pieces. No, not just 4 pieces. I have 1, 2, 3, 4 log base 8s. 2 of them are negative, and I can see that this 4 comes from this power, this 3/4 comes from this root, and so forth and so on. Why I'm trying to tell you all of this right here is that in most of these cases, you can literally skip to the answer by just being very careful when you're looking at your log. If I have log base 10 of x squared multiplied by x squared multiplied by y to the 4th power divided by z to the 1/8 power multiplied by m to the 6th power, right here, I can immediately write the answer. Well, when I distribute the log to this one, that's going to give me 2 log x, right? Again, it's not distribution, it's really expanding the log. Then when the log expands to this one, it's going to be positive 4 log of y. When it expands to this one, it's going to be minus 1/8 log of z. And then when it expands to this one, it will be minus 6 log of m. And just like that, instead of doing all of that unhappiness and joy I was doing a while ago, I can go ahead and then just put it all together nice and succinctly. And what that does for us is the reverse operation makes the reverse operation very nice and neat. Sometimes they give us many logs and they say write as a single log or combine into a single log. So they might say combine into a single log, or they may say write as a single log. Doesn't matter either way. And so let's say I have 5 log base 2 of x minus 10 log base 2 of w plus 3/4 log base 2 of k. Well, the first thing I need to note is that are all my bases the same? Because none of this works if their bases are not the same. And so they are. And so what I have to do is kind of think of this backwards. So what I have right here is my log base 2. I know some of them are going to be in the numerator and some of them are going to be in the denominator. And I look right here. Notice that this is positive. So therefore this goes to the numerator and it's going to be x to the 5th power. Because when I distribute the log 2 to this right here, that's the term I'm going to get. Then this one is negative, so it goes to the denominator. And so then that's going to be w to the 10th power. Remember the 10 comes from the power up here. Then I got my 3/4, this is a positive, and so then I'm going to go multiplying by k to the 3/4 power. course, we don't write 3/4 power, we write it as a radical. And so our answer is simply going to be log base 2 of x to the 5th, the 4th root of k to the 3rd power over w's 10th power. Like so. Alright, one more example. Let's say I have log base 5 of x squared minus 9, and I am subtracting log base 2 times log base 5 of x plus 3, and I want to go ahead and write this as a single log. I want to go ahead and simplify this. Well, both of these are log base 5, so that's good. Both of these are log base 5, so that's great. And so I know it's going to be equal to log base 5 of, well, the x squared plus 9 will be in the numerator. My denominator will be x plus 3, but I know that the 2 will come up and be the power squared. So I have an x squared minus 9 over an x plus 3 squared. So with this right here, I can go ahead and simplify some more because I can factor on the inside. This right here will be equals to log base 5 of x plus 3 times x minus 3 divided by x plus 3 squared. And of course the x plus 3's will cancel out. So this 2 and this x plus 3 cancels out. And so my final answer will be log base 5 of x minus 3 divided by x plus 3. So I have taken this log right here and I have rewritten it as a single log. The last thing we need to look at right here is when we have complex expressions that we want to simplify. So let's take an example. So the question will be given that log base 3 of 4 can be represented by the value a, and log base 3 of 7 can be represented by the value b. Can you write log base 3 of 28 squared in terms of a and b? Well, first things first, I want to expand this logarithm. That's what they're really asking me to do, is to expand this logarithm. But I only see a 28 in here, so what do I have to expand? What you have to do is you have to go off into your working column, and you got to take the number 28 and you have to break it down to its prime factors. Well, 28 is 4 times 7. Well, I could break the 4 down some more, but I notice right here that there's a 4 right here, and so 4 is the number I'm looking for. So I'm not going to break down the 4 anymore. Although you could have, it would still take you to the same place. And so right here, what this is saying is log base 3 of 28 squared is equals to log base 3 of 4 times 7 squared. So now, I can break this log up. I take the 2 to the front, and so that's equals to 2 multiplied by log base 3 of 4 times 7. And then the 4 and 7 themselves break up, so this is 2 times log base 3 of 4 plus log base 3 of 7. Again, when you're multiplying, this splits into 2 separate logs. Again, you're kind of distributing the log 3 in. I should say expanding the log 3. That's a better term right here. I distribute the 2, so that's 2 log base 3 of 4 plus 2 log base 3 of 7, and of course log base 3 of 4 is the letter A, log base 3 of 7 is the letter B, and so this equals 2A plus 2b. Ah, 2a or 2b? That is the question, I think. Who knows, right? Alright, one more example. Express y as a function of x. C is a constant. And the expression is ln of y is equals to ln of 5x plus ln of c. Well, I see that plus sign right here, which means I can combine these two logarithms with multiplication. Remember, the plus sign means multiplication. And so this is ln of y is equals to ln of 5cx after I multiply. And at this point right here, I have two strategies to solve. I'll show you the hard way and then I'll show you the easy way. The hard way is to get rid of the ln by knowing that its inverse is e, and so you take e on both sides. So when you take the e on both sides, the e and the ln cancel out. And so it tells me y is equals to, and then the e and the ln cancel out, 5cx. The other way of doing it is the same thing, but it's more straightforward. Well, if the two sides are equal, then the arguments must be equal. And so therefore I just don't need the ln's. And I could just, break out my ninja stars and defeat the ln's in a single swoop. And that leaves me y is equals to 5c. Another example of this type, express y as a function of x. If I have, say, ln y is equals to x plus ln c. So again, I'm trying to solve for y. What I'm actually going to do first right here is take the ln c over. So minus ln c. And so I have ln y minus ln c is equals to x. And now I have a division right here. And a division means subtraction right here. And a subtraction means division. I think I just gave it away. Oops. And so this is going to be ln y over c is equals to x. In this case right here, I do not have an ln on each side. And so I do have to take the e on both sides, the e. E and the ln cancel. So y over c is equals to e to the x. And the last step is to multiply by c to cancel the c out. So times c, b cancel. And so y will be equals to c multiplied by e to the x. Again, where c is a constant. More preferably a positive constant. But c is indeed a constant. Alright. Good luck.